Hello. We now have another talk from Vivek about bootloading. Vivek.
Hello. Okay. Right, so for those of you who do know a lot of technical stuff and know how all this bootloading works, I'm probably going to say things that are like approximations of the truth or flat-out lies. Please keep the illusion of my competence alive and don't contradict me until the questions at the end. Yeah, so this isn't going to be deeply technical, but what I'm going to talk about is the boot flow of SteamOS and on the Steam Deck right now, but that device we didn't even know existed when we started this work, so it wasn't targeted specifically at that. But I'm going to walk you through how we designed it and why we designed it that way, and hopefully that's of some interest. So our story begins like more than 5 years ago. I actually checked the first commit on the bootloader, and it was 5 years ago tomorrow. I know I did a couple of months of research before that, so we'd been talking about it before then. But we'd been planning a major update for SteamOS. It had been stagnant for a while. We hadn't really done anything with it, but we were looking at sort of major changes we wanted to make. You know, a big step, not just a small evolutionary change to it. And one of the things that came up out of that was we wanted the new version of the operating system to support atomic updates. Because the idea was that it was targeting at things that were going to be used as a game machine in someone's home. Was our idea at the time. Again, we did not know that this thing existed. We had no idea that this was in development, if it even was at the time. We were just noodling around and coming up with ideas. But this has a couple of implications, but first we'll go through what an atomic update means. So what is an atomic update? Basically, it either completely works or it doesn't. When you update the operating system, you have, in our case, 2 operating system image slots. You update the one you're not booted on, you try to boot it, and if it succeeds, glorious success, that's the new current slot, you go on using that. If it fails, you go back to the previous one and say like, well, that didn't work, try again later. The idea being, again, if it's a consumer device in someone's home, they don't have to worry about a partial update, something breaking, a config file needing to be done. We replace the whole operating system at once, and we completely roll back if that doesn't work. So this does have some implications for how you design it, how you do the layout of the operating system, and how the bootloading works. So what are some of those implications? So each image should be self-contained. It should be as vanilla as possible. We don't want to have to change the layout of the operating system image itself much. Ideally it should be bootable on its own outside of the dual slot boot environment, so it makes it easier for development and testing and debugging. Yeah, I just said that, independently bootable. Those are the things you need to do, and you need to design your bootloader flow to allow for that. How do we do that? Well, it turns out we take the universal solution. We add a layer of indirection. Solves all your problems except the one about too many layers of indirection. So we have a stage 1 bootloader, which has just one job. Pick an image to boot based on whatever your decided criteria are, and hand over to it and boot. Stage 2, the operating system loader, is pretty much what you'd find in any generic operating system. It does whatever it would normally do, and it really doesn't know anything about there being another slot or that another bootloader handed over to it. So it allows you to develop your operating system as you normally would, but then put it into this environment where you have this failback, which I think is quite nice for the end user. So that's the management review of how all this shiny, glorious future technology works. But we're not those people, so let's dive into some of the details of what that means for your boot process. So bootloaders these days, at least in the x86 world, are UEFI. What is that? Well, it lets you use a PE32 Plus Windows executable as a bootloader. It provides a sort of weirdly mushed together small kernel plus libc-like layer, like it does those functions for you, so you don't have to do everything for yourself like you used to do with old-school Int13 bootloaders. It looks very strange if you're used to anything like POSIX-ish, like properly weird, but it is still much nicer than the old way of writing bootloaders. Like, I complain about it because it's my job, but I wouldn't go back to the old way. And so we're going to need to do a few things to get this to work, so let us count our yaks. For this setup to work, we need the UEFI firmware, what used to be called the BIOS and still is, although that's not really what you're supposed to call it, to start our stage 1 loader. We need our loader to find the other boot partitions, which are part of these self-contained operating system images. We need to choose the right one out of those, somehow, we'll get to that, and we need to start that bootloader and have it do all the things it would normally do as if none of the preceding stages had occurred, because we don't want it to know that ever existed. So let's go through those and see how they were achieved. So, UEFI, how does it boot things? Well, it either boots a location specified by an NVRAM variable. There's a lot of detail in there. It can specify all sorts of things, but basically it says, for our purposes, look at this partition, this location, boot whatever you find there. Or there is a well-known location on the first boot partition it finds, and it just boots that by default. Great, so we can use either of those solutions, not a problem. This yak practically shaved itself. Fantastic. This is going to be plain sailing, right? There are going to be no more problems. So, let's go to the next step, listing the other boot partitions. So the API to do that, good news, the API is there and is mandatory. Fantastic. We can guarantee that anyone who has a vaguely compatible UEFI implementation will have this. But it is an unusual use pattern. Like, at the time, I was still exploring and experimenting. I thought, like, will it work? I mean, it's supposed to work. Reading of the documentation implies that this should work. But at no point do they guarantee it works. And also, this is not how most UEFI boot processes work. Most of them follow the very simple state of go to the default location or the configured first location, boot whatever you find there. They don't have to deal with other partitions being there. They don't have to find them from within the bootloader. They don't have to do any of that stuff. So it should work. Does it? Like, I tried it. It worked. Fantastic. Big relief. Because, otherwise things were going to get complicated. And we'd made promises to the customer, which is, one of those things. But still, another yak shaved, So, how do we pick the image we use? Can we use NVRAM variables? Well, it turns out sometimes, not reliably. Some of the test kit I had, which was just generic PCs at the time, didn't reliably keep its NVRAM variables. Some of them had firmware that just decided, I don't know what those NVRAM variables are. They don't look right. I'm going to scrub them and put what I think Windows should have there, which was a great one because there wasn't Windows on the box and it immediately stopped booting. So, and also a lot of firmware updates erase the NVRAM variable block, which means you immediately forget all of those configuration variables. Not fantastic. So, didn't look like a good solution for us. Now, what about configuration files? Are they going to work? Well, again, the API is there for opening files on FAT file systems, which is what the UEFI boot partition is. And it's pretty easy to do from the operating system, like setting NVRAM variables from user spaces. It's doable, but it's not nice. So we kind of went with this approach. Like, it looks like it's reasonably easy to do from both sides that we care about. Let's do that. And we designed a config file, which has various simple key value pairs. The important one that we ended up on was boot requested at, which is basically recording the time that this partition set was requested to be booted. And the file with the highest, so we have a config file per image, and the file with the highest boot requested at wins, which means the last one that requested to be booted boots. That's good enough for the demo, so yak shaved. 3, the next bootloader. So we need to open that image's bootloader, which in our case in the operating system we're using is grub. It's fine, it's reasonably well understood, but it could be whatever it uses. An advantage of this design is we don't really have to care what the next stage bootloader is. Like, when we found it, we can go to that partition, we can go to the well-known location there because we define it, and we say, like, just boot whatever's there, which means you have completely isolated your stage 1 bootloader from the operating system, you can completely rip up what's in there. Like, it could be a completely different operating system with an entirely different bootloader. Our stage 1 loader would not care. As long as the config file was correct, it would do the right thing, and your system would boot, which gives us a lot of liberty to make horribly breaking flag day changes in the user space visible operating system, which is great because it means we don't have to link the two closely together. Like, the development can decide one day we're going to change everything, and we'll be like, that's fine. I don't care what you do in there. I just need to get to the starting point. We need to sanity check the contents of what we found to make sure it actually is a bootloader, or at least something vaguely executable looking. We need to launch it. And yeah, there we have it. Minimum viable Yaks shaved. This bootloader thing worked. All of that worked. And once we got around the weird NVRAM variables being scrubbed, we were ready to demo it, and we demoed it, and then that got baked into the product. So I then had to maintain it. You know, a rookie mistake, but you know, it's one I keep making. So that sounded easy. There were some stumbling blocks along the way, of the fun variety. So there was, at one point, we think, a weird compiler bug. Now remember, we're compiling an ELF executable and using bizarro obj copy hacks to make a PE32 executable out of it. So there's a lot that can go wrong in there. So given that, I'm surprised this only really cropped up once. But at one point, we had a function that only worked if it was declared static, even though it was being called from, like, it's not dynamically linked. It was called from the same file, it's the same executable unit. We don't know why that didn't work when it wasn't declared static. It wasn't even being called outside that file, so we just called it static, had a drink, and moved on with our lives. Flaky UEFI implementations. This is where the real fun begins. So at one point, I started getting reports of weird crashes. Sometimes weird crashes in the user space operating system after it had booted. And it took a long time to figure this out. And it was some of the UEFI implementations I was testing on, so did not correctly handle opening the same file twice at the same time. So you opened it in one bit of the code that needed to open a directory, look at what was in there, do some checks, hand over to another bit of code which said, right, I'm opening this file in this directory, and then closing it at the end. And it turned out, on some implementations, but not others, the first close just marked those data structures as gone inside the UEFI implementation. They got released, went on with our lives. Other UEFI functions used that memory space to put their data structures in. And then when we got to unwinding things later, and we tried to close those, I'm going to call them file descriptors. They're not, but let's call them file descriptors. We freed the wrong data structure, which corrupted the UEFI boot services and runtime services, which meant that later, after the operating system had booted and tried to call the runtime services, you got a kernel crash. That one, I mean, the workaround was we'll just implement reference counting for all of our file opens and closes and make sure that any resource that we do that allocates a data structure is ref counted. So if we look like we're opening the same thing again, we'll just give you the old copy we already have and not throw it away until we get the final close. But that one took a while to figure out because, you know, it was very strange. Secure boot was fun and games because it turns out when we, few slides back, I said we launch it. Like, that's easy. There is the equivalent of exec or execute a loaded thing in UEFI. You can't use it if you're using secure boot. If you're using secure boot, you have to open your next executable, do the relocation from the disk layout to the memory layout by hand. This is immensely painful. And then jump to its entry point. You can't use the normal launch functions. I don't know why it's designed that way, but that's how it works. It's deeply annoying, and it's incredibly hard to work out, because if you get one tiny thing wrong, all you get is just a dead machine, and of course you have no debugger or fallback here. You just have to go like, well, I guess I did something wrong, I wonder what it was. Yeah. So what I ended up doing was implementing a pre-allocated file on the UEFI boot partition into which I wrote log messages which were numbered so I knew their sequence. And when I reached the end of that, to avoid filling up the partition in case I had a runaway sequence, it just went back to the beginning and started writing there. And because they were sequentially numbered, I got to see that. So good old printf debugging effectively for us. I think there's theoretically a way to attach a debugger to a UEFI executable, but it looked hard, and I just didn't have enough time or enough rum to attempt it, so I didn't. Yeah. So, mission mostly accomplished. We have achieved a first-stage bootloader that is simple, ish, silent, and invisible to the user. Like in all of the reports that came out after the deck actually launched and people were playing around with it, they were all saying, well, what bootloader does it use? And everyone just said Grub. Nobody even knew the first bootloader was there, which I personally take as a compliment. And obviously, because we've done this, and that was all easy, right? So stretch goals, because obviously we can't ever have anything simple. We have to make life hard for ourselves. So it turned out we wanted a simple text menu to allow people, developers, whoever, if they triggered it, to pick which image slot they booted. Just in case there was a problem with one slot or you were debugging or trying something out, you want to give people a way to do it. So UEFI does provide a text console. It's pretty much what you expect a fairly primitive console to look like. You can register a key handler, so we can pick up the up and down arrow keys and move along the menu. And that allows us to put together a simple menu that allows us to list which config files are available and say, I want to boot that one, please. It's great. But UEFI, and this is one minor step backwards from the old bootloader technique, there is no key down or key held detection. You can register a key handler. It will tell you when there has been a complete key event. If you hold down a key from start of boot, it will not tell you. It has no way of telling you. So you must either have your vendor do something custom in firmware, or you have to find some other way of triggering it. You can have a flag file on the boot partition that the bootloader looks for and says, like, oh, I should display a menu. You can set a volatile NVRAM variable to say, like, please show a boot menu this time. Or you can get your firmware vendor, if they'll talk to you, to implement something custom to tell you that the user held something down during boot. I've set a variable to let you know that this is going on, so you trigger the menu. I mean, the other option is you can have a delay, which is why Grub has the delay, because it's the only way to reliably pick out when a user is pressing a key, because you have to give them time. And all of this is really fast. I've never had the log file go across the 1 second boundary for all it does. So, there really isn't time for the user to hammer a key and have it register. I tried it. I could get it to go, maybe one time in 15 if I was really, really fast with a key. So it really wasn't an option for a device that's ending up in users' hands. So that's what we ended up going with. Obviously, having done that, we decided our lives are still too simple. So can we have a mode in graphics menu in graphics mode? Well, there is a frame buffer and a fairly basic blitter, but that's basically all there is. You can choose the graphics mode. It tells you where the frame buffer is, and you can blit rectangles to it from memory. You've got nothing else. That's it. Then you can't output text to it either. If you're in graphics mode, you can write text to the text console, but where it ends up is left to the conscience of the individual UEFI implementer. Some of them mangle the text on top of the frame buffer in a semi-readable way. Some of them send it to another monitor if you have one that's in text mode. Some of them just don't send it anywhere that I can tell. Some of them put it on the serial console. There's really no way of telling where it's going to go. So we can't combine the text mode with the graphics mode in any useful way. So how do we do it? Well, we use PFF2 fonts, which GrubMcFont makes, which basically takes your standard fonts on the system and pre-renders some bitmaps from those, somewhat hinted, into a PFF2 font. So, that's great, because it means I can just use GrubMcFont to prepare a font, and I don't have to do the work myself, which is always fantastic. Then you have to render them pixel by pixel into a memory buffer that you've allocated yourself. taking note that PFF2 fonts don't all give a fixed size rectangle. They have a rectangle which is only the bits that are set in the font. And I understand why they've done this, because otherwise the font would be even bigger than it is. But it means you have to read the offset, and when you render the font, go like, push the rendering down. So you're really having to count your offsets into your allocated buffer. And then you blip that to the frame buffer, which fortunately that part at least worked as advertised. And that's how you get text onto the graphics mode console. And while I was at it, I decided, since I didn't have these things, and the idea was to let the users label their boot slots with anything. So, yes, indeed. Well, they're not in the font currently because I haven't baked them into the font, but you could have emoji on the boot screen if you gave a source font that had them in there when you prepared the font. I tested that. It did work. UTF-16 is because the bootloader uses, is unclear from the spec. One of UCS2 or UTF-16 is what it uses. I've never had to wander into the parts of Unicode where you would actually care about the difference, but I implemented UTF-16 because it was easy to find what the compliant spec was, including for malformed sequences. Same for UTF-8, which means we can now have properly internationalized text. You can write your own name to the boot slot, even if you use non-ASCII characters. It's fantastic. It works. And there we have it, a graphics mode menu. It was both more and less work than I expected, because largely because of the PFF2 fonts thing, where I could just, whenever I got randomly jigsawed text on the screen that was at the wrong heights, I could go like, well, why is that happening? Look at what Grub was doing and go like, oh, right, okay. Well, I guess that makes sense. And then boot failure detection. Like, this is not actually just shininess. This is actually useful. So what we had here was, I said the stage 2 bootloader did only what the OS normally did. That is now a lie. I have it do slightly different things now. Mainly, I have it increment a boot counter in the config to say I've made whatever the previous number of attempts was plus 1 when it gets handed over to. And the operating system then decides when it reaches a certain target. It could be the graphical mode target. In our case, it is the graphical mode target. You could do further tests, like you could test whether sound is working. Like, you could play sound out through the speaker and see if you detect it through the microphone and say, yes, the sound level works. This is a successful boot. You could do anything you want there. And if those tests are satisfied in the service that implements this test, you set that counter back to 0. So the next time the bootloader boots, it goes, 0 attempted boots that didn't complete. We're good here. If the counter is too high, stage 1 bootloader can say, you've had, in our case, it's 3 failures. I think something's going on here. You've had 3 attempts to reach user space, not succeeded. So I'm going to show you the menu, and I'm going to print the number of boot failures and when the last boot failure was at the bottom, and then you can choose the other image if you want. It also labels them in the menu to say which is the current boot slot and which is the other, so you don't have to remember. That's basically the lightning tour of how we arrived at the design of the bootloader and how it all works. Any questions? And before you do, bear in mind, before you ask me any really complicated, deep questions, that I'm just the guy who was standing around there when someone asked a question if something was possible, and I said, yes, that sounds possible. Again, bit of a rookie mistake, but that's basically my whole career, so, I can't really complain. So, any questions?
Thank you for an excellent talk. My sympathies. A lot of this gave me interesting flashbacks. But one thing that I was thinking of when you were talking about debugging was last time I did this was probably in the BIOS, in the actual BIOS days.
Right.
But I remember at one point having some luck with attaching a QEMU debug stub to the other end of what I was trying to debug, so that I had something to step through, and I was really, really confused.
Yeah.
Does any of that still work on UEFI?
Maybe. I mean, you can boot QEMU with UEFI, but it's a different kind of executable. I mean, I assume it all sounds like, this is going to be one of those answers I regret giving. It sounds like it could be made to work, but fortunately, because you do have enough support to write to a log file, you can resort to the printf shotgun, which was a lot less work in this instance. So that's what I did.
How do you avoid the situation where you've got two OS images?
Yep.
How do you make sure that OS image 2's bootloader doesn't accidentally boot OS image 1's root file system or vice versa? Do you re-ID the images when you're imaging or something?
No. So when we install the grub config file, it has the partition that it's going to find, because when we install the image, we root into it, and we prepare the grub config files. They get installed onto... So you have the ESP, which is the boot partition,
Right.
but each
Yes.
OS image has its own pseudo ESP. It's the same type of file system, so it only sees that, so it writes its config there.
And you inject the IDs into that during the imaging
Yes.
process?
Yes.
Yeah, that makes sense.
Yeah.
Some UEFI implementations were bad and some were worse.
Yeah.
Which ones were which?
They were just some no-name boxes we had lying around the office, because at the time we didn't have any custom hardware. We didn't even know custom hardware was in the offing. Like, we'd just been asked, can you do like atomic updates, and this all kind of fell out of that, because, well, okay, atomic updates, therefore we need two images, therefore we need something. Turns out NVRAM variables won't do the job for us. Much sadness. We need something more complicated. So we had some no-name boxes sitting around in the office, and at the time the brief was make this work on generic hardware. So I tried with the generic hardware we had. And yeah, I mean, like, I found these bugs, and I was like, well, the chances of the vendor caring about this are less than zero. I can't fix it. I just have to live with it. So that's what we did.
So you say you put the boot attempts counter, you
Yeah.
increment that in the stage 2, did you say?
Yes.
Why don't you increment that in your part in case the OS's bootloader the image's bootloader is broken?
You can do that. We thought about it, and it was basically, we figured, like, if the stage 2 bootloader is actually so broken on both slots that it's not going to boot, we're realistically going to ask the user of this consumer device to return it to base. We could put it in there. The other reason was, at the time, the design was, this decision changed later, but at the time the decision was that the stage 1 loader was only ever going to read config. It was never going to write anything.
Right.
So that decision did change later, so we could now do that. We could have different counters for each stage, so we'd know exactly where it failed.
And then if you somehow had a broken update, you could fall back to the working image, and the user wouldn't have to return it to base.
Yeah. So, yep, we could do that. In practice, it hasn't. In practice, the only people who've really broken their systems that much are the ones who have turned off the read-only file system and hacked around with their systems. That we had one report the other day of a failed update, which turned out to be because the user had made their ESP partition somehow NTFS. So yeah, when we got to the end of the debugging chain and found out that that's what had happened, we said, yeah, okay, pal. Honestly, we're kind of impressed, but also this is your problem now. You can fix it or you can return it to base, but we're not fixing it for you.
So, secure boot.
Yes.
How were you signed? Are you signed using a specific key from the firmware vendor?
No. It turned out, after talking people through everything we'd have to do to get it working, and since we were going to make, by that point, the device had actually materialized, and the decision came down the pipe that, you know what, we're actually going to make this completely open and people can install whatever they want on it. So at that point, we just said, we're only going to release it, tell people how to turn it off anyway, so we'll just not do that. Which meant I got to throw away a very complicated code branch, which was both sad and happy.
If you had to do this again, now understanding that there's a piece of hardware and who is going to use it, will you have considered using core boot instead of UEFI?
It depends on, well, the thing is, the idea is it's got to be generic, so we are going to release at some point when we finish shaving all the remaining yaks that need shaving. This thing, so we'd probably have to support like whatever was most common, because the idea is that we're going to give it to people and say, here, if you can boot. So the idea is that people will be able to install SteamOS. And Valve have said this. The plan is to install a generic release a generic version of SteamOS that's not just deck targeted.
But I think you can still have UEFI on top of core boot.
Okay. I have not looked into it. I'm not going to say no, but we just haven't really thought about it.
And I guess also one of the reasons you don't write in a stage 1 is because then you cannot boot Windows using because Windows won't be able to write 0 when Windows is ready.
Yeah.
Your boot count.
Yeah. Well, I mean, we can still boot other operating systems. Like you can set the NVRAM variables, so people do dual boot their decks. We need to look at ways to make that sort of more robust, so that it's easier for people not to screw up their systems when they're setting up. Because people go out and they find bad advice from Stack Overflow about how to do this, that does result in either people having to completely reimage their devices, or if they manage to break it sufficiently hard, return it to base. We do want to make it easier. We haven't really figured out all the things we need to do to make it easier yet.
Thank you.
So, have you released all of this as open source yet?
I think the bootloader is, I think it's open. Like, we haven't advertised it heavily, but if the repos aren't available, then certainly the source tarbles of what gets released are.
Okay.
So, and the plan is to open them, but there's a bunch of auditing and things that need to happen first.
Oh,
so.
sure. No, obviously, I'd be really keen to have a look.
Yeah.
No, not just to have a dig, but just to see how you manage some things.
Sure.
Sounds awesome.
Okay. That looks like it. So I'll move into the next talk.